Good morning, everybody. Happy Thanksgiving week. Quiz sheets, right? You can get those turned in if you haven't done that already. Yes, they're only out of 20 because your teacher failed and didn't give out enough points. I just take like my total, which was around 80, and I divide by 4. So that's where that number came from. And apparently I did it last time I taught 2B because it's been 20 points per semester. So at least I'm consistent. Today, what we're going to do is we're going to try and finish up, I think it's chapter 31, so that we can do all of 32 tomorrow. And what's on the agenda for today is radiation, the units that we measure radiation in, and hopefully by the time you walk out of that door, I can convince you that radiation isn't all bad. We'll see if that is true or not. All right, so to kick off this discussion, let's return to our periodic table. On the periodic table here, maybe you'll remember, I said that anything over atomic number 82 was naturally radioactive. In other words, the nucleus is so big at that point that it can't hold itself together, and it is going to decay in some way, shape, or form. It's either going to be an alpha decay, a beta decay, or a gamma decay. Who locked it? I probably forgot that. Sorry, Truman, we're not trying to make fun of you.
I was like, am I not allowed?
Not anymore. So anything over lead is naturally radioactive, right? Bismuth, polonium, antimony, and then everything on this lowest level right here. So what ends up happening is, and this is just one of the three what we call naturally occurring decay series. All elements that are more atomic number than lead will eventually become lead. It's just a question of how long it takes and how many steps does it take to get there. Don't panic here. You don't have to memorize any of these decay series or any of that kind of stuff. I just wanted to just point out, right, that the transmutation of the elements, right, going from one element to another happens perfectly naturally for elements like uranium, right? Uranium's down here, atomic number 92. It's going to undergo some decays to get to lead, right? Its eventual endpoint is going to be lead. And I think, I've got this is the thorium decay chain. Thorium is, sorry, I started you off on the wrong one. Thorium is right here. So uranium will decay to thorium. And how does it get down to atomic numbers? Which kind of decay is that? It's alpha decay. Okay, so it undergoes an alpha decay to get to thorium, and then it will go through another series of decays. Okay, thorium, we could follow this chain, thorium to radium. All the purple lines are alpha, and all the blue ones are betas, but as you'll see, it'll kind of go through there. Now, when we talk about half-life, right, the statistical measure of how long it takes something to decay, uranium's first alpha decay, the half-life on that is 4.5 billion years. That's billion with a B, right? Okay. So the Earth has been around for about that long, and so the Earth contains half of the amount of uranium it originally had. Side note, slight tangent. Why is the Earth's core molten? Where's the heat coming from? It's coming from radioactive decay. Okay, the reason we have a liquid core is because our planet's big enough to hold on to that heat and not dissipate it too fast. And the radioactive decay in the elements in the Earth's mantle and core are continuously generating that heat. So we have an intrinsic source of heat within our planet, which is a good thing because the core creates our magnetic field, which protects us from the fusion explosion that is our sun. and so on and so forth. So when anybody asks you where does the heat come from to keep the core liquid, it was the heat of formation, so the amount of energy it took to bring the planet together in the first place, plus the ongoing radioactive decay. We should have, just by heat of formation, we should have run out of heat about 1 billion years ago. But the fact that we have a continuous thing means that it's being driven by something, and that something happens to be radiation. These other decays usually have much shorter half-lives. It's that first one that generally takes the longest, and especially in terms of like uranium. All right, so now we get down to what does it mean to be exposed to radiation? How much radiation does it take to kill you, give you cancer, blah, 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 blah. And then how do we go about like measuring and quantifying that? So we need to, again, be careful about our wording here. Remember, radiation to a physicist means any electromagnetic energy. Okay? In the case of the alpha and beta, those aren't electromagnetic waves, they're particles. They are radiating from the nucleus and they're carrying energy, but they're not EM waves. And so we're not going to be talking about, like, it gets confusing again. We will talk about gamma rays because gamma rays are photons and they're actual electromagnetic waves. But what we're talking about today is is ionizing radiation. So in physics, we specifically refer to the radioactivity that everybody thinks of when it comes to the Hulk and three-eyed fish and, you know, Chernobyl and all those things. That's ionizing radiation. It's energy that's being delivered via alpha, beta, or gamma radioactive sources. So that's what we're talking about today. And I'm not going to apologize for the system because I didn't invent it, but I do perpetrate the crime. There's a lot of units floating around when it comes to measuring radiation and radiation exposure. So, and this is further confused by the fact that there are two different systems. There's the SI unit system, and then there's the stupid unit system. Okay, so. And we do, I mean, strictly speaking, we've already talked about becquerels and curies. Curies isn't a US unit. It happens to be the one that's in the use in the US the most. But both becquerels and curies are part of the SI designation. But I split them out here just based on usage. A lot of what you'll read about, even all over the world, depending on how old the text is and all that kind of stuff, or if the website's not up to date, even internationally, you'll hear people using rads and rems. That's because the United States sort of led the way in all of the nuclear science in the 40s and 50s and 60s and 70s. They were really on the forefront of that. The Sievert and its associated SI units really didn't start coming into common usage until the 1990s, 1980s, 1990s. And so the world's been a little bit slow to pick up on the SI units. I, of course, expect you to be able to talk any of them. But let's break this down, okay? Because there are three different ways of talking about radioactivity. There's straight up activity, and activity is literally like it's a count. We're counting the number of events, the number of radioactive particles, okay? That's what activity is all about. You can detect, like a Geiger counter detects activity. It can tell you that there's a alpha, beta, or gamma ray present, but it can't tell you which one it is. And so I'm talking strictly about Geiger counters. There's other kind of counters like the one I'm going to show you in a minute. They're called scintillation counters, and they can tell the difference because they can actually directly measure the energy of them. So activity is an event, right? It's counting the number of radioactive things, which is different than a rate. A rate would be the number of events per time. So I didn't put that unit up here, okay? but you can have becquerels per second or curies per second. And I already mentioned that like the curie is, I can't remember what it is. It's like 10 to the 14 becquerels or something. Where's the curie? That number right there? Yeah, I don't even have, I can't even find it in my notes. What was it, Jay?
I have 3.7 times 10 to the 10 second.
That sounds good. So that's curie, one curie is equal to 3.7 becquerels. Okay. And was that an event per time? Decays per second? Okay. So that does have it. That is a time unit in there. All right. Then we get to absorbed dose. And this has a couple of different names. It can be absorbed dose. It's also called absorption. Okay? The key thing that you need to understand about this unit is that 1 gray is equal to a joule per kilogram. So the gray is measuring energy per mass. It's not just straight up energy. It's the amount of energy that was absorbed by a certain amount of mass. So if we know like the target, the thing that got exposed to radiation, if we know that it is, say, 10 kilograms, okay, and we know that we gave it 100 joules of energy, then we would take 100 joules, we'd divide by 10, and we would get 10 grays. So the gray is this way of measuring energy per mass. And then there is the dose equivalent. That symbol right there is a sievert. I can never spell this. S-I-E-V-E-R-T, some person's last name, okay? And a sievert, okay? Key thing here is that a sievert is equal to, let's get rid of the 1, I don't need the 1. A sievert is a gray times something called the Q factor. It's also called the RBE factor. Q or RBE, depending again on which country you're in. RBE is relative biological effectiveness. And the Q factor is the Q factor because it doesn't sound as scary. Okay? So the word biology just got inserted into the discussion. We all know that ionizing radiation has an effect on cells and cellular metabolism and can cause errors in DNA and DNA replication, which can then lead to cancer and other problems. The Q factor or the RBE factor is an attempt at sort of quantifying the type of radiation, whether it's alpha, beta, or gamma, and then also like what part of the body that radiation impacted. So if a radiation worker, somebody that works in an environment where radiation is used all the time, like an X-ray machine or a CAT scan or a nuclear power plant or something, if they get exposed to a certain absorption or a certain activity of radiation, it really matters if that exposure was like in an extremity, like in their hands or their arms, versus, say, their chest or their head. Like, what's the difference between arms and chest? Organs, right? There are no vital organs in your extremities, okay? All of your vital organs are right here. And so we need to know not just how much energy was involved, but also what kind of radiation it was and what part of the body it happened to hit. Now, RBE concerns itself a little bit less with what part of the body. There's other factors that you can use in other units that come into play. These are the only ones that you're required to understand. But so you can do a shortcut for this class, and like the Q factor or RBE, that just tells you whether it's alpha, beta, or gamma. And we'll kind of use our little sort of shorthand, like alpha can't get through the skin, beta can't get through clothing, gamma is going to get you anyway, right? We'll use that sort of idea as a proxy for like what part of the body it's hitting. Because we're not going to get in, there's a lot, there's like whole semesters worth of being able to learn how to measure these kinds of things and what effect it has medically on an individual. So to be able to convert, right, between sieverts and grays, you need to know the Q factor for the type of radiation that you're getting. The other side of this table, the US unit side, the imperial unit side, you can see that there's really the only disagreement here is a factor of 100. So I tend to work on the SI unit side, and then if I need to communicate to somebody in the American system of units, I'll just multiply by 100. Right? Okay? Or divide, depending on what it is I need to do. Okay? So 1 gray is 100 rads, right? If I have 10 grays, it means I have 10,000 rads, right? So just be aware, right? Just kind of, you might want to just have this table on your cheat sheet. It's the only way I've ever been able to organize any of this information in my brain. A gray and a rad are measuring the same thing. They just argue about like where to put 0, right? The sievert and the rem are measuring the same thing. The rad, that stands for radiation absorbed dose. So, that, it's an acronym. It means something. And then REM is radiological equivalent in man. So you can tell this was invented in the 50s, right? So that's where those units are coming from. But like I said, more and more nowadays, we're hearing, even in the United States, the use of sieverts and grays. The thing about units in radioactivity, whether it's REMs or RADs, whether it's grays or sieverts, is that these are units that have 2 associations. One, people have either played Fallout or watched movies or TV. And so they have this kind of oogie boogie nature of radiation, and whenever a RAD or a REM is like talked about, oh, somebody's going to die, right? But then there's just the basic, like, chances are you've heard of REMs or RADs, but probably not sieverts, right? Or grays before today, right? So there's just basic, like, unfamiliarity with the unit. And so when a scientist comes out and says, well, there was 10 to the minus 6 sieverts of radiation exposure, the general public has, like, no concept of how much that is. When Fukushima Daiichi melted down after the earthquake in Japan, was that 2010? And the reactors in Japan melted down. I say not me, the scientific community, the monitoring stations. I'm not sure people are aware of this, but like radiation is measured and tracked in all of our food. So samples are pulled from all kinds of whether it's like spinach from the field, strawberries, milk from cows, meat from cows and chickens, and like it's all like sampled and tested to make sure not only that it doesn't have parasites, but also it's sampled for radiation. When Fukushima Daiichi happened, about a week later, it took about a week for the radioactive cloud to kind of make its way across the Pacific. There were elevated rates of radiation in cow's milk. And of course, all the news outlets on the West Coast picked up this story, and there's radiation in cow's milk, right? And they would quote the amounts, okay, of radiation in cow's milk. And the problem was they never provided a scale for like how tiny the amount of radiation was. It was being measured in picosieverts. 10 to the minus 12, right? Okay. As you're about to see, a microsievert is common background radiation. So we're detecting, our ability to detect radiation is far outstripped, right, our understanding of how bad radiation or good radiation can be. And as I'm about to show you, your biology requires radiation in which to function. So the fact that we were measuring radiation, great, we're able to track it, but it was so low. But what do you think people did with this information? Stopped buying milk, right? Okay. Now, there's a lot of problems there, right? For some segments of our population, milk is a great source of both calories and protein and nutrition, right? A kid that's eating Hot Pockets might get some good nutrition out of a glass of milk, right? Okay. Especially for growing human beings, milk is a kind of a good idea. Although my pediatrician growing up had a button that said milk is for baby cows, because he was anti-milk. He was a pretty funny guy. And then, so anyway, people stopped buying milk. They started buying up, iodine pills. One of the things in our physiology is that our body confuses iodine with cesium. They're chemically similar to each other. And cesium is a radioactive byproduct from a nuclear disaster. And so cesium comes around, your body will incorporate the cesium. If you take a bunch of iodine, you can actually flush the cesium out of your system, out of your thyroid. And so people were buying, and all of the supply of iodine pills got like snapped up. Okay, and then of course people were charging too much money for it online and all that kind of stuff. So then people started buying iodized salt because the salt has iodine in it. The problem is I calculated it out. You'd have to eat something like, I can't remember, was it 2 or 4 kilograms of salt per day? A kilogram is 2.2 pounds. So we're talking about eating anywhere from 4 to 6 pounds of salt per day to get the equivalent dose of iodine that you would get, say, from an iodine pill. What would happen to you if you ate 6 pounds of salt in a day? You die. You just simply die, right, from salt poisoning. Okay? So yeah, again, units are important, right? Okay? But so if I come out and say, oh, there's a bunch of sieverts everywhere, right, then it can really start to get kind of scary. So here are some of the Q factors or RBE factors. And this is kind of, I always felt like this was backwards, but we'll do an example here in a second where you see where hopefully it'll make sense. Notice, right, that the safer the radiation, and by safer in quotes here, I'm talking about alpha particles. Why is an alpha source safer than a gamma source? We can kind of stop it with our skin, right? As long as we don't like ingest it or inhale it, right, get it inside of our skin, we have natural protections against it. In fact, alpha rays, when they're coming off of something, really can't go more than like half a meter through the air before they get stopped by air particles. But it has the largest Q factor, right? And you would kind of think that the bigger the Q, the worse it is. Actually, it's the other way around. Again, I'll show you about this in a second. But the bigger the Q factor, the less devastating the exposure is going to be. Gamma rays and X-rays are almost always given 1. They are, again, up there with the worst kinds of ionizing radiation. And yes, X-rays can ionize ionize atoms in your cells and cause problems. This is why when I will fight every time a doctor orders a CAT scan for me. Does anybody know what a CAT scan is? Well, you sit in the tube, but it's not an MRI. Okay? So a normal X-ray, they put you on the thing and they take a single picture, maybe 2 or 3, depending on the angles that they need. And any one individual X-ray, as you'll find out, and we talk about like how to scale these units, any individual X-ray isn't that big a deal. In fact, the dental X-ray is probably the least amount of exposure you get from an artificial source, right? It's not very big, and they don't even need to leave the room or put on the lead vest for dental X-rays. They do it to make people feel safe. Okay, so it's all about what we call safety theater. And An X-ray by itself, not a problem. You can have like 20, 30 X-rays a year and not be exposed to anywhere near your maximum amount of radiation. Okay? A CAT scan can take 100 X-rays in a very short space of time. Because what it's doing is it's taking slices. It takes an X-ray as it slices, depending on which way they're slicing, but like say through the head, right? So they can slice this way, but they can also slice this way, depending on what it is they're looking for, right? And so they'll take an X-ray, and then they'll move and take another X-ray, move, take another X-ray, all the way up, okay? Now, the problem is you've just had 20 to 100 X-rays taken, right, of, say, your head. I had to have septoplasty, which is my nose had a deviated septum, and I was like, there was 10% open airway on one side, right, okay? And I was having all kinds of sinus infections and things like that. And they had to go up there. But prior to that, the doctor ordered a CAT scan. I was like, why? And she's like, well, I need to see the structure of your head so I can do the surgery correct. I was like, okay, that's fine, right? But if they're just ordering CAT scans willy-nilly, you can get exposed to a lot of radiation really fast in a CAT scan. Great for emergency medicine, great for preoperative, right, diagnostics. But we don't know why you're sick, go get a CAT scan. You want to start asking questions, right? So X-rays are in there with gamma rays as being a fairly nasty form of ionizing radiation. But again, that really depends on the power of the X-ray. Because like I said, dental X-rays, they're not worth worrying about at all. You can get dental X-rays all day long and be just fine. All right, so let's just, I just wanted to take you through being able to like do calculations with these units. Remembering, right, that grays and sieverts are pretty close to each other. It's just that a sievert includes this way of talking about whether it's alpha, beta, or gamma, right? A gray is all about energy. It's energy per mass, right? And then working our way through it. So let's see here. So we were given a mass of tissue, and we know, what's the little m in front of the sieverts mean? It's a milli. So this is a 0.8 times 10 to the minus 3 sievert dose equivalent. And it says gamma radiation. So what's our Q factor? It's 1. Okay? It's the one I always remember. All the others, I'm like, well, I can't remember what a beta or an alpha is. And beta and alpha, again, depend on like, you'll see different Q factors given for beta and alpha, depending on the situation. But we know our Q factor is 1. And they want us to find the dose in REM and then the amount of energy that was absorbed. So let's do part A first, okay? If we go back over here, how do we get from sieverts to REM? It's a factor of 100, right? 1 sievert is equal to 100 REM. And so now we are back to a chapter 1 unit conversion problem. So I've got 0.8 times 10 to the minus 3 sieverts. And in every 1 sievert, there's 100 REM. So I'm just going to basically multiply by 100 here. And I'm going to get 80 millirem, or 80 times 10 to the minus 3 rem. Okay? So going between sieverts and REMs is just a factor of 100. And hopefully that's not too hard. Hopefully the hard part there is like, wait, what's a sievert? Right? Go back to the table, right? Sieverts and REMs are the same thing, right? They're dose equivalents. They involve the Q factor. All right. Then they ask us how much energy was absorbed. So which of these units has got energy in it? Yeah, it's the gray, right? It's a joule per kilogram. So we now need to know how many grays of radiation were received, okay? So to figure that out, we've got our Q factor of 1. And we know that back on this slide here, right? A sievert and a gray, right? A sievert equals a gray times the Q factor. So a sievert is equal to a gray times Q, or in other words, grays is equal to sieverts divided by Q, and our Q factor is 1. So what does that mean for our grays? If we got 0.8 times 10 to the negative 3 sieverts, how many grays did we get? Same number, because the Q factor is 1. So the amount of grays we got is 0.8 times 10 to the minus 3 grays, right? And then, well, here, I'll do the full calculation. Sieverts divided by 1, the Q factor being 1, right? So this is 0.8 times 10 to the minus 3. And then how do we find the energy? The total amount of energy? We need to know the mass. And we do know the mass, don't we? Right? Because a gray is a joule per kilogram. It's an energy per mass. So to solve for the energy, I'm going to take the grays and I'm going to multiply it by the mass of my sample. So the amount of energy is going to be my grays, 0.8 times 10 to the minus 3 sieverts, grays, same thing in this case, times 0.5 kilograms of tissue, and that's going to get me 0.4 millijoules of energy. All right, let's do the same thing, only we're going to do it for alpha particles. Okay, for alpha particles, what's the Q factor? We're going to use 20. These are sort of the standard go-tos. If you don't know what the actual value is, you go with these. Okay, so our Q factor here is 20, right? So when we go to calculate so does the calculation change as far as like REMs and sieverts? No, right? That calculation doesn't change. That's going to stay consistent because there's no Q factors in this, right? It's just a straight calculation back and forth, okay? So, we did find the dose and rem, okay? So that stays the same. It's only this part that's going to change because of this Q factor right here. So we're going to run the same calculation again, only we're going to do it with our new Q factor, right? So the amount of grays is the amount of sieverts, which didn't change, divided by the Q factor. So I did that, and this is 0.04 milligrays. Okay. And then to get the amount of energy, right, I take my grays, 0.04 times 10 to the minus 3. I multiply by my mass, and I got 0.02 millijoules. Okay? So the 0.02 millijoules that's right here is 20 times less energy than the 0.4 millijoules that was given by the gamma rays. Okay? So it should come as no surprise, right? If the Q factor is different by 20, then you get 20 times less absorbed dose, right? You get 20 times less energy in the dosage. My expectation for you is in all of these units is that, number one, you remember chapter 1, okay, and be able to divide by 100 to get from REMs to RADs and sieverts to grays, but also that you understand the difference in the what the units are trying to do, right? A gray is all about energy per mass, and a sievert is all about quantifying what kind of radiation it is and what kind of impact it's having on the target. Becquerels and Curies, that's really used in half-life stuff, right? So that you'll see those units in half-life calculations. So That's where that one is used. Okay. It's time to go dark a little bit here. Okay. How much does it take to kill you? Like let's scale this, right? And give you an understanding of like how much a sievert is, like what's a microsievert, what's a millisievert, all those different kinds of things. So what I've done is I have separated this out in both sieverts and rems. Again, there's only a factor of 100 difference here, right? And we just have to, the thing I remember is that I need less sieverts to be in trouble, right? See how sieverts is smaller than rems, right? And so I always remember that fewer sieverts is equivalent to larger amounts of rems, is how I kind of remember that. Okay, these are taken directly from OSHA guidelines for exposure to radiation. OSHA, of course, governmental body responsible for keeping track of worker safety. Let's see here. Annual exposure to the general public. So OSHA distinguishes between the general public and then jobs that give exposure to radiation on a normal basis, radiation workers. And I've already mentioned things like X-ray technicians, people that work in labs where radioactive sampling is either done, used, or implemented in some way. People that are exposed to the radiation. So you can be using a machine that uses radiation, but if that radiation is contained, you are not classified as a radiation worker. But anyway, there's the general public and then there's specific people, right? And it's kind of interesting, right? Annual exposures from what? As you're about to learn, the ground is radioactive. The food you eat is radioactive. The people around you are radioactive. Radiation is a natural thing, first and foremost. We can artificially cause it to happen, and there are artificial sources of radiation. But much of the radiation that you are exposed to on an everyday, every year basis comes because you live in an ecosystem where radiation is present. Okay, and then there's a legal limit to the amount of exposure that the general public can be exposed to. Okay, and this upper limit is supposed to take into account things like X-rays and medical diagnostics and possible exposure to radiological events, that sort of thing. The problem is most doctors have no idea how many X-rays you've had in a year. And there's no body or corporation, hospitals are not required to keep track of how many X-rays you get in a given year. The good news is that you'd be hard pressed. I think it's 3 CAT scans of the head per year, and then you will be up against this legal limit of radiation exposure. Okay? So unless you're being involved in a lot of accidents, okay, you're probably pretty safe and can have, I think I saw one time that it's like 17 chest X-rays of equivalent, right? So don't get tuberculosis, right? But again, nobody is keeping track except maybe the patient, right? This patient does. I keep track because I've been taught about radiation exposure and I don't want too much of it. Luckily, I don't need too many X-rays too often. Okay, but notice how much you need to. Okay, let's go over here. This number might be easier to work in our brains, right? So to observe a health effect, and notice this has nothing to do with radiation sickness, right? But like for a doctor to be able to detect that radiation, somebody's been exposed to radiation. What is that? Is that a factor of 4? 40? That's 40 times the amount of radiation. The legal upper limit is 40 times smaller than the amount that a person needs to be able to actually measure the effects of radiation on biological tissue. Okay? So even though maybe you get 3 CAT scans or 17 chest x-rays a year, you've hit the legal limit, but the legal limit is so much lower than the actual limit where you're starting to see problems, right? But usually the patient doesn't even know there's a problem. The doctor has to kind of be going, wait, there's something weird going on here, okay? Then, a factor of 4 bigger than the minimum observable health defects, and you're starting to get radiation sickness. Radiation sickness is nausea, sweating, vomiting, fever. All of this sounds like the body's reaction to any kind of like poisoning or any body system that's got out of whack. Your brain doesn't know whether it's motion sick, poisoned, been exposed to radiation. It has no way to detect any of this stuff. All it knows is that some body system is not right, and so it's going to react the same way to get rid of whatever the problem is. And how do bodies get rid of things like viruses and bacteria? Pee, poop, or throw up a lot, right? Sweat a lot. Get the temperature up. Get the immune system roaring so that we can go attack this thing, right? Your body can't distinguish between what's causing it. All it knows is that it's got a response, and this is the response it's going to take. So, but notice, right? Before you even start getting into the realm of cancer, okay, you have to be twice the exposure as being able to detect radiation sickness, okay? So, like, the Curies were somewhere between these two values, the minimum observable health effect and radiation sickness. They never reported problems with digestion or vomiting or nausea or any kind of thing. They always talked about the radiation burns that they were getting on their hands that they didn't know were radiation burns. Okay, and then if I walked into the back room and I found a 5 sievert per hour source of radiation and I exposed this entire room for an hour to that, then statistically half of you would die due to that radiation exposure. Let me be very clear here. You wouldn't just drop dead because I exposed you to radiation. It's just sometime in the future you would die, and that death, you could draw a straight line between the exposure and the reason that you died. Okay? 10 sieverts or 1,000 rems, make plans because you are going to die. That is a lethal dose for anyone. And at that high a dose, depending on how fast you receive it, it can be exceedingly miserable on your body. So let's talk about radiation and kind of where it comes from. And I want to do a demonstration that I hope is going to help you sort of scale and categorize and realize that you can walk out that door and be pretty safe. Okay, no matter where you're going, notwithstanding all the radiation that might be around. You'll notice that I am putting on protective gear, PPE, right? And the PPE I am wearing has nothing to do with the radiation that is in this box. Okay, this is my box of radiation right here, okay? And has everything to do with something else that I have to protect myself from in this box. That is not radiation. We'll see if you guys kind of put in the back of your brain, what is Mr. Balogh scared of in this box, okay? So inside of this box, I've got a lot of things, okay? All of the things in this box, in some way, shape, or form, are radioactive. And what I've got here, a bunch of little plastic discs, okay, that were made by Oak Ridge in Tennessee. Oak Ridge is a national lab that does nuclear They build nuclear materials for power plants, for weapons. It's one of the labs that was set up during the Manhattan Project. But all of these plastic discs are NRC exempt radionucleotides. So radionucleotide is a fancy word for a nucleus that's radioactive. NRC, the National Radiation Council, is the group that under the Department of Energy that's responsible for keeping track of radioactive substances in the United States. So NRC exempt means the NRC doesn't care that I have these, right? They're outside. NRC could care less, right? Whether or not I have these radioactive substances. This one is cesium-137, got a half-life of 30.2 years, and is a gamma emitter. Thank you. Polonium-210, alpha emitter. Show that around the table. Don't eat it. Tellurium-204, 3.78 year half-life beta emitter. So we're covering all of the things here. Okay, you guys get beta. Go. You get gamma. You're the only one, so your exposure is higher. Let's see. Should we give you guys alpha?
Yeah, of course.
Okay, there you go. Right, they're scaredy cats. They don't want it. Okay. All right. So what do we got here? All right. So I just gave you a bunch of radioactive samples out there, right? Okay. NRC exempt radionucleotides, meaning that the NRC doesn't care that we have them, and they're not tracked in any way, shape, or form. And no, you can't sue me for giving those to you because, quite frankly, they can't hurt you. And I can prove it in a court of law. All right. Let me get this out. There we go. Okay. This right here, okay, is a thermoscientific, okay, RADI B20ER survey meter. This is it's not a Geiger counter, it's a scintillation counter. So this can measure, right now it's measuring in units of microsieverts per hour. So this device as a radiation detector is not only detecting the presence of radiation, it can tell what kind it is. And on the fly, calculate the dose equivalent. Remember, absorbed dose was energy per mass? But this thing can correct for alpha, beta, and gamma and give you sieverts, right, per time. So this is kind of measuring a rate. Excuse me. What this device is used, the people that use this device are first responders. So firefighters, police, anybody that's responding to any kind of natural disaster, industrial disaster, any of that kind of stuff. If you need to know whether or not you are dealing with radiation, you will be carrying one of these. This is about a $1,200 unit. They're pretty expensive. You don't want to break the window right here. This is the detector part right here. It's got this plastic outside to it, okay? But I can wander around and I can measure, right, the amount of radioactivity that's coming off basically anything. Okay? So let me turn this. You can't see the display. I could read the numbers out to you, and that would be kind of boring. But there is a mode here. Just like the movies, right? Okay. Every one of those little blips is a what? It's the detection of a radioactive particle. So I ask you, where are these radioactive particles coming from? Everywhere. Okay? They're coming from the sun. They're coming from you. They're coming from the walls. This building is primarily made out of concrete and metal. Where does concrete come from? The ground. The ground is radioactive. You are radioactive. Why are you radioactive? Where did you come from? My mommy and my daddy. Okay. But you had to eat something, right? And the thing that you ate, where did it come from? The ground. Even the cows came from the ground because the cows have to eat the corn which came from the ground, right? And the ground. So nature is naturally radioactive. Substances that are naturally radioactive, like carbon-14, like uranium, like radium, like radon, all of these different things, right? It doesn't have to be bigger than lead. It just has to have too many neutrons in its nucleus, right, in order to have this thing. So carbon-14 is in the air. I mean, you can't get away from it. And what you're hearing is normal background radiation. It's the radiation you are in all the time. Okay? So now let's start measuring the ones I gave you. What'd you guys get? This was the gamma emitter, cesium-137. Everybody drops their little disc now, right? Okay. But as you can hear, right, from the detector, okay, is it elevated? Yeah, definitely elevated. See how I go away from it and I get the background again, right? That was an elevated amount of radiation. Okay. You taking pictures for your lawyer? Okay. Not as much, right? Okay. This one has a half-life of 138 days, and that is probably 25 years old. So it's more or less the same as background. This one, the beta emitter, 3.78 years. Again, barely over background. Here's strontium 90. More than the first one? Sounds a little bit faster than the first one, didn't it? Okay. Okay, we're finding out who the losers are today. So they're pretty close. One was 9 microsieverts per hour, and one was, this one's 11. Okay, so that was 7. That was 9, and this one's 11. What was this? This was a gamma. This is cesium-137. That, just like that cesium-137 over there. And then this one's dead because it's an alpha emitter, right? Very short half-life. Okay, so let's see. Which one was the worst?
Mine.
Yours. Okay. Okay, so there's the worst of the NRC-exempt radionucleotides, right? These are man-made, human-made, artificial radiation sources. We convinced, in this case, cesium-137 to exist, right? And it's radioactive, and we made it to be that. It can occur in nature, but this was produced, okay? So it's an artificial form of radiation. So you get the rate there, okay? About 11 microsieverts per hour. A micro would be 0.000001. And you're getting 10 from that sample per hour. How radioactive is this? Not at all. But it sounds scary, doesn't it?
Yeah.
Right? Okay. Can you see what this is? It's a rock. Okay? This is a rock. Okay? This rock happened to be picked up off of the ground. Okay? This rock has a lot of granite in it, and granite is one of the highest uranium-containing minerals in geology, right? In our classification of the different kinds of rock and all that kind of stuff, okay? So this was picked up off the ground somewhere, I think, on the eastern side of the Sierra Nevadas. It might have been in Nevada, which might explain a lot, right? Okay, but that's a joke. This is natural, okay? When you go up to the mountains and you sit on a piece of, some nice soft piece of granite, right? You are irradiating your rear end, okay? Right? Because granite is just very radioactive. All right. So here's the reason that I wear all of the protective stuff, okay? And it's this little box of joy right here, okay? Does anybody know what I'm peeling off of this box? Nope. This is lead, okay? This is why I'm wearing the gloves and the eyes, and I should probably wear a respirator too, okay? Lead can give you lead poisoning. It affects your kidneys? Liver? Everything? It's a neurological problem, okay? The reason I've wrapped this one in lead foil, and it's the reason I'm wearing the glove, because I don't want lead poisoning, okay? 318 microsieverts per hour, okay? This, I'll just walk around with it. Can you see how it's slightly green? It's a rock that's kind of got a pretty green sheen, okay? This is uranium ore, like not pure uranium ore. This is actually granite that just has a really high concentration. This came out of a coal mine, okay? Yes, right? You see that little green right there, okay? Yeah, nothing, okay? So that came out of a place underground that does have a higher than normal concentration of radiation, right? Okay. So NRC exempt, nature's best effort, right? With that being a more normal, like getting close to granite rock kind of exposure, okay? When was the last time anybody was admitted to the hospital due to radiation poisoning from granite? Never. Okay? Now, if you're down in the ground mining, I don't know, radiation or anything else, you've got bigger problems to worry about than radiation. Because coal miners and other miners underground, what do they die of? Usually respiratory failures of some kind because of the particulates that they're exposed to. Either coal or beryllium. Berylliosis is really nasty. It dissolves all of your lung tissue. So yeah, there's other problems, not just the physical cave-in ones, but other health effects that happen when you're down mining coal in the ground. So what I wanted to show you there was that radiation is both man-made and natural, okay? That natural can really kind of be off the scale, so to speak, compared to some of our man-made sources. It just all depends on how much, when, and where, okay? So you got cosmic rays, you have the ground, you've got other humans, okay? In fact, if you sleep in bed with a partner for a year, your radiation exposure is higher than if you slept alone. Anybody want to sleep divorce? Let's not talk about smoking because smoking's dumb, right? But basically in smoking, what are you doing? Inhaling. Besides killing yourself. You're inhaling what? Radiation. Why are you inhaling radiation? What's in a cigarette? Tobacco. Where'd tobacco come from? You're just basically inhaling radioactive particles on top of the tars and the nicotines and the other things that are going to kill your alveoli. All right, okay? Just looking at cigarettes alone, the radiation alone, right? It's all kinds of problem. Notice that man-made sources, medical, TV not so much anymore because we have the flat panels. The old TVs that were the glass, right? That's a beam of electrons that's pointed at your face.
The ones with the
Curved glass on the front, okay. Coal power. Why is coal power on here?
Are you talking like trains?
I'm talking about coal-fired power plants. Why are they a source of radiation? Where does coal come from? The ground. And you burn it, and it goes up the stack. Now, there are certain things that are, well, actually, they're not tracked anymore, thanks to Trump. But we used to track like sulfur, carbon dioxide, all these different things that are coming out of these power plants. What was never tracked, ever, was the amount of radiation coming out of a coal power plant. The amount of radiation coming out of a coal power plant is something like 20 to 30 times higher than a nuclear power plant. Because a nuclear power plant, there are regulations keeping track of the radiation, right? And so it's illegal. So basically, like one of my favorite things is olive oil. Olive oil is pretty radioactive. Why is olive oil radioactive? Because it makes you glow. Because it comes out of the ground. It comes from olives, which come out of the ground, right? By law, this isn't written this way, but this is if you take the law to its extreme. things can go into a nuclear power plant, but if they're too radioactive, they are not allowed to come back out. Salad dressing. If you bring your salad in your lunch and you work at a nuclear power plant, you have to eat it. It cannot be taken back out. Because technically, the olive oil is too radioactive compared to what's allowed to be coming out of a nuclear power plant. Olive oil is like 20 times high beyond the limit of what can come out of a nuclear power plant. Now, the government doesn't stop people from taking their lunches in and out. It's fine, right? But that's kind of the point, right, of the regulations surrounding nuclear power. They're very strict when it comes to radioactivity. But coal power plants, nah. Go ahead and poison people and expose them to lots of radiation. This is the sort of a visual version. Notice that, like, where does most of your radiation exposure come from? From nature, okay? It's from all around you. You can't get away from it, nor would you want to. It turns out people get sick when they're exposed to too much radiation, but they also get sick if you're not exposed to enough. Your physiology changes. Your immune system starts to freak out if there isn't enough radiation around. You evolved in a radiation environment. I was going to say radiation rich, but it's not too rich. You evolved in a radiation environment. Your physiology depends on it. And so to be removed from it can be a problem as well as being exposed to it. Like most things, it's the amount that matters. Okay, to finish off here, I wanted to show you this chart. Now, it's really hard to see on the screen, which is why I'm about to zoom in on certain sections of this chart. But I wanted you to see the whole chart. This was written by XKCD. This is a web comic. The guy's name just totally flew out of my brain. He's a really smart guy. He does a lot of sort of science-y based cartoons that make you laugh and then make you want to cry. Randall Munroe, that was his name. Randall Munroe of XKCD. After Fukushima happened, Randall Munroe was getting upset at the coverage of the radiation. Again, I kind of mentioned this, right? Where the news coverage was blowing out of proportion, the amount of radiation. So he came up with this chart that is a 2-scale diagram of the amount of radiation you are exposed to from various things. It's a graphical representation of all the numbers I've just told you. So what I'm going to do is I'm going to zoom in on the blue section. And again, it's kind of hard to see, but we'll make our way through, okay? So this one blue square represents sleeping next to someone, okay, for a year, 0.05 microsieverts, okay? Living within 50 miles of a nuclear power plant is equivalent to 1.5 people. Here's the coal power plant right there, six blue squares, okay? Why is it 3 times higher than living near a nuclear power plant? No regulations for radiation on the coal power plants, okay? Eating 1 banana is twice as much as sleeping next to somebody for a year. Bananas are America's favorite fruit. By far, Americans eat, more than 50% of the fruit sold and consumed in the United States is bananas, right? Apples don't even touch it, never mind peaches, any of that kind of. Bananas is the answer, okay? Now, if you're into any kind of health, exercise, all that kind of stuff, why do you need bananas? Potassium. Very high, naturally occurring amount of potassium in bananas helps with muscle function and avoiding cramps and all that kind of stuff. Potassium is radioactive. Specifically, potassium 40 has a half-life of 4.7 billion years. Bananas give off positron decay. It's the type of beta decay it's not an electron, it's a positron, okay? Bananas give this off like crazy. are we running around telling people to not eat bananas?
We should be.
No, because bananas are perfectly safe. Yes, they're good for you. Okay? Back in the 1970s, nuclear scientists, chemists and physicists, put forth to the international United Nations body that's responsible for like sorting out unit systems, who, by the way, still isn't doing a good job, and said we want to define a new unit of radiation, and we want to call it the banana. We want the public to be able to understand, right, that, you know, a chest x-ray is so many bananas. I can't remember what the number is, right? Or holding a piece of granite is so many bananas. Like, a banana has radioactivity in it, right? And then your exposure was now 10,000 bananas, right? They were shot down because the banana lobby, the fruit lobby in the United States, was upset that fruit was being associated with radiation. And 3 Mile Island and all that kind of stuff, right? So this actually happened right after 3 Mile Island because, again, the radiation release from 3 Mile Island was nothing. Okay? It was an amount bigger than zero, but it wasn't anywhere near health effects, right? And yet, from that moment forward, the public became afraid of radiation. And again, for no reason, right? I think 3 Mile Island was like 150 bananas or something like that. It was really low, okay? And so it was that attempt, but the unit has only survived amongst physicists and chemists. We still use it kind of internally as a joke, right? So yeah, and it's been revived a little bit. Have you guys run into, it's kind of a meme, banana for scale? Have you heard about that? Okay. It's a reference to the old bananas unit for radiation and for general size of things, but the banana is just very handy. Okay, so eating one banana is 2 blue boxes, okay? And here's an arm x-ray. 1, 2, 3, 4, 8, 10 bananas. Equivalent. 1 arm x-ray. Okay? This is what you get from standing in the state of Colorado. Natural background radiation, several bananas. Call it 15 bananas, right? Why? Huh? Why am I picking on Colorado? No, it's a good state. It's higher. There's less atmosphere between Colorado and outer space than there is, say, between Fresno and outer space. And so their radiation exposure is going to be higher. Currently, my parents and my daughter and my sister and my nieces and nephews, my brother-in-law, they all live in Colorado. Am I worried about them? Not in terms of radiation. Wildfires, I am, but not radiation. Dental or hand x-ray, and here is standing, okay, for 1 day. This is 1 day's worth of exposure standing in the town of Fukushima, which is near the Fukushima Daiichi power plant that melted down after the earthquake in Japan. Is it elevated? Yeah. Okay. But it's just, what, 30 bananas? Don't eat 30 bananas in a day. You'll have other problems. Okay? But like, is there that much radiation? No, there really isn't. Because this is what you get flying from New York to LA. Okay? Here's a normal background dose received by one person in 1 day. This is just being alive, living in buildings, going out in the sun and going, oh, the sun feels so good. What are you doing? You're soaking in radiation of all types. All types. Not just the, oh, it feels good ones. Okay? So this is what you get flying from New York to LA. What do flight attendants get exposed to every year?
A lot.
And yet, do they wear radiation badges? No. Not because we don't care about flight attendants and pilots, but because the amount of radiation is too little to worry about. It's not going to cause health effects. Now, there is an exception to that rule, and it's for pilots and flight crews of the long haul. I'm talking like 10 to 14 hour flights, like flying from here to Australia or whatever, right? Okay. There is a limit to the number of flight hours they can have in a year. And they cannot exceed that number of flight hours, not because of fatigue, but because of radiation exposure. If a pilot or a flight crew, and by flight crew I mean the stewards and stewardesses, if they exceed, I can't remember how many hours it is, but if they exceed that amount in a year, they have to be given desk jobs. They have to be grounded for the rest of the year to keep their radiation exposure down to acceptable limits. And again, it's all because of radiation exposure. There's rules that a flight crew can't work for more than 10 hours, I think, at a time, continuously before they have to be relieved by another flight crew. So like planes that are flying for more than 10 hours have 2 sets of pilots on board. The stewards and stewardesses apparently can work as much as they want or are told to. But flight crews have to be relieved. That's an attention. That's a fatigue thing. Apparently it doesn't matter if you're fatigued being served your drinks. Okay, so what we're going to do is we're going to take, so again, I'm coming off of this big chart here, right? So we were just looking at this blue part right here, right? So I'm going to take the entire blue section. The entire blue section is equivalent to 3 green squares. So add up all of this blue, okay, and you get those 3 green squares. So here's living in a stone, brick, or concrete building for a year. Okay? Here's the average dose to somebody living within 10 miles of 3 Mile Island. The nuclear power plant that did go critical in New Jersey, but the reactor plant people saved it, did a wonderful job getting that shut down. And by the way, they're thinking about turning it back on because of AI, because of the power consumption by AI. Okay? So notice this is total dose living within 10 miles of 3 Mile Island, and it's about the same as living in a brick home for a year. So again, elevated, but nowhere near problem. Okay? Here's the natural potassium in your bones. Here's the limit that can come out of a nuclear power plant in a year. Nuclear power plants can release radioactivity. In fact, the 3 Mile Island incident, they released radioactive steam in an effort to get the reactor under control. The amount of steam that they released was very small compared to the legal limit that the EPA allows a nuclear power plant to release. Okay? And here's your yearly limit that I specified on that other chart, right? Where it says that there's like a yearly amount, right? Here it is in green boxes, okay? And here's the maximum dose any one person got from 3 Mile Island. That was one of the workers at the plant who went in to inspect what was going on, right? So again, we're far away from any of these things on a normal thing. But then this one really starts to make me think. That's a mammogram. Right there. Okay? About, I want to say now 12, 15 years ago, the American Medical Association changed the guidelines for mammograms. Before this, the guidelines was as soon as you turned, what was it, 40, 50, something like that, a woman was told go get mammograms on a yearly basis. Okay? They changed this, like I said, 10 to 15 years ago to say don't do this anymore. Because 2 things were happening. Number 1, you're raising exposure to radiation. A mammogram is a very uncomfortable procedure, but beyond the discomfort, it is something that exposes you to a lot of radiation because they're taking a lot of x-rays. Okay? So it was causing increased radiation exposure. Notice, here's the EPA limit for radiation exposure. So this like from a power plant or man-made source, that's the legal limit. And for medical diagnostics, it's okay to exceed that, right? Here is a chest CT scan, right there. So they go in looking for tuberculosis or something, okay? Bigger than a mammogram, okay? So the second thing that was going on is that the mammograms weren't giving false positives, but if you go in and you look for trouble, you're going to find it. As we age, tissue just starts to harden, things happen. And in breast material, prostates, different kinds of organs, like I've talked with my doctor about this. I'm a 51-year-old white male. I probably have prostate cancer. I do. Like basically anybody that's got a prostate that's more than 30 years old probably has prostate cancer. It's simply a question of like how much, right? All of my tests, everything indicate that my prostate's healthy and nothing's going wrong there. My father-in-law has much higher elevated tests. He has prostate cancer, but again, they're not going in to rip it out because it's being managed, right? It's simply a question of like what the cancer is, what type it is, and the problem with mammograms is that it was giving too many women things to worry about. They kept saying, well, we see something. And then that starts to change lifestyle, all kind. It snowballs. And so the current I'm not a doctor, I just play one in class. The current recommendation is to get mammograms. If your doctor says that one is necessary, you should ask the question. You should say, okay, for what, why? Why are you saying this? And if they just say, well, because you're old, that's the wrong answer, okay? If your family has a history of breast cancer, get mammograms. It can save your life. But if there's no history and you're healthy and you do your self-exams, okay, then you're going to be all right, okay? Follow your doctor's advice, of course. Gentlemen, testicular cancer, very similar idea, right? If a doctor orders any kind of scan, ask them why. And if it's just because, well, you're older, right? Might not be the right reason to do it. So, mammogram, chest, CT scan. Here's 1 day dose standing 50 kilometers away from Fukushima. Here's your normal background radiation from totaling up all of the sources, right? So natural sources, man-made sources, all that kind of stuff. So this is the normal background radiation. It exceeds the radiation exposure for a single member of the public. Again, radiation exposure means unnatural sources, like a man-made, I'm going to go get my radiation to expose you to it, right? So this is the normal background. This is a mammogram. This is Fukushima. How big of a disaster was Fukushima? Radiologically speaking. It was nothing. Okay? It was bigger than 3 Mile Island, yes. But what haven't I showed you yet? Starts with a C, ends with Noble. Chernobyl. This right here represents the maximum dose permitted by law for anyone that works in radiation. And again, that's below the minimum observable health effects. Take all of these greens, put them together, and shove them into that many orange boxes. Okay? So this big thing of green boxes right here, which was the maximum limit, can be summed up in 5 red boxes. Okay? That's the limit that a radiation worker can be exposed to in a year by law. This is the amount of exposure that you need in order to have a clear link, right, to increased cancer risk. Notice this does not say you're going to get cancer, but an increased risk of getting cancer. Cancer is always a roll of the die. Okay? This is what you need for radiation symptoms. Okay, so this is the yearly limit for radiation workers, but this is what you need for symptoms. This is where it gets really dark. This box over here always scares me. Okay, dose limit for emergency workers protecting valuable property. This is written into the law. An emergency responder, a firefighter, police, paramedic, search and rescue worker, whatever, right? There is a dose limit if you are protecting valuable property. It is the same for increased cancer risk. So you can, it's okay, you can have increased cancer risk if you're saving valuable property. I don't know what that is. A dog? I don't know. Okay. Dose limit for emergency workers in life-saving operations. It's roughly half of receiving radiation poisoning. Again, written into the law. So there is a legal limit between which an incident commander has to say, you have to stop saving people's lives. Severe radiation poisoning, fatal dose, no matter what, you're gone. This one you might survive. Take all of the orange boxes, shove them into one spot. And this is what standing next to 10 minutes next to Chernobyl was like. Both Chernobyl and Fukushima as disasters are rated incident level 5 on the scale of radiological disasters. That's because level 5 is the highest. And it fails to capture how different Fukushima and Chernobyl were. Okay? Chernobyl was orders of magnitude. We're talking 100 to 1,000 times more radiation released than Fukushima. Way more. Okay? Did this one have the, there's 3 Mile Island. I thought there was one for, no, there wasn't. Okay? You can actually go and calculate your average background radiation. You don't have to measure it. You don't have to keep track of it. You can just go calculate it. This is based on statistics for like where you live, what kind of building you live in, all that kind of stuff. It's all available for dosing. These are examples of doing radiation on purpose. I've had this done to my GI tract. They give you a radioactive emitter. In my case, I had to drink it. I thought it was hilarious because the rad tech came to me. He's like, so what flavor do you want? I was like, what? Because you got to drink this awful, it's a barium sulfate solution. And sulfur compounds taste like rotten eggs. They're just awful. And so he's like, yeah, what flavor do you want? I was like, it comes in flavors? He's like, oh yeah, no, there's chocolate, vanilla, and strawberry. I was like, it's barium sulfate. Does it matter? He's like, no, that's just what we tell people so that they feel better. I was like, give me all 3. He's like, you got it. So yeah, it tasted really bad. So you drink it, you kind of roll around, you wiggle around to try and get the stuff to coat all of the insides, and then they start taking x-rays. Okay, they were trying to see what was wrong with my GI tract at the time, right? But you know, because normally the gooey bits inside of you, x-rays don't care about them, right? They go sail right through. But if you put this contrast agent in, you're able to see like what's going on inside of the soft tissues of the GI tract. On the right here, okay, is iodine that's been injected into the bloodstream, and they're imaging the vasculature within the brain, right? So again, great, I mean, you're exposed to radiation here because now you have a radioactive emitter in your bloodstream or in your GI, right? The half-lives of it are very short, meaning it's very radioactive. There's a lot of radiation coming off, but because the half-lives are short, the radiation disappears within minutes to hours, depending on the contrast agent that they happened to use. One last just little piece of information. What's this machine called? This is an MRI, I'm pretty sure. This isn't a CT scanner based on its thickness here, okay? CTs tend to be a little bit like narrower, okay? The ring doesn't have to be as big. This one is an MRI, and I can tell because the ring is bigger because it has to house the magnets. MRI, what does it stand for? Magnetic resonance imaging. It used to have a different name. It used to be known as NMRI. What was the N for? Nuclear. They stripped the N off because people were scared of the nuclear word, right? Now, it was called nuclear because what an MRI does is it essentially takes picture of the nuclei of atoms. It's taking advantage of an effect where the nucleus can align itself in a very powerful magnetic field because the nucleus has a magnetic field just like bar magnets do. And the big powerful magnets would force the nuclei in your body to line up, and they all point in one direction, and then they slam it with radio waves. And those radio waves would cause the nuclei to like kind of wiggle. They'd like kind of not flip, but they go boing. And the rate at which they kind of came back and settled it back into the magnetic field told the machine what kind of nucleus it was. Was it hydrogen? Was it oxygen? Was it phosphorus? Right? Okay. And based on getting the boings out of the nuclei, they were able to image all the parts of the body. Soft tissue, hard tissue, didn't matter. They could figure out what it was. And again, we have a way of looking inside of a person without having to cut them open. This is a piece of miracle equipment that should, I mean, if your doctor says, I want to get an MRI, your answer should be yes. Because there is no ionizing radiation in this device. Even though the word nuclear is in it, okay, it's all about the nucleus. There's big magnetic fields, there's radio waves. Claustrophobia is a problem, as is noise. These things are noisy. They sound like jackhammers while they are working. They make you wear earplugs or earmuffs or something, right? It sounds cool. But you have zero ionizing radiation exposure while you're inside one. Every time they say we want a CAT scan, I'm like, can I get an MRI instead? And they're like, yeah, it's not as detailed, but it'll work. I'm like, I'm in. I go running for the machine. I dive in, right? Sit still. I've had to have cervical MRIs, and they put you, it feels like you're back in the Middle Ages because they put you in one of those Iron Maidens, those cages. They have to put a cage around your head and your neck to not only keep you from moving your neck, but they need to direct the radio signals kind of down the axial part of your, anyway. And so you're inside of a very small space, which I kind of like. I'm like, you're sitting, the only problem is they're jackhammering. Otherwise, I could take a nap, right? I'm on a memory cushion mattress. I'm in a nice, small, contained space where nobody can bother me, right? I can take a nap. And then they just go, bah, 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 right? They start hammering you with radio waves. And you can hear it. You can hear these radio waves being formed. So anyway, yeah, get MRIs. Don't be afraid of them, because even though they have the word N in their name, they have nothing to do with ionizing radiation. Well, if you have pieces of metal inside of you, you got other problems. So yeah, you don't want to go near one of these. All right, that's all I've got. I'm on track for being able to finish everything tomorrow. So chapter 32 tomorrow. Fission and fusion, bomb making 101 tomorrow.